Okay, so we have now talked about buoyancy and pressure when the water is sitting still. Okay, so that is fluid statics. Now we have to talk about fluid dynamics. And essentially, what we're going to be talking about is this idea of the water flowing through a tube. We are going to, in all of our calculations, discuss flow rate in a pipe or a tube that is completely filled with water. Okay, we're not going to have any air in there because that causes some weird things happening to the way it flows. Volume flow rate is given the letter Q. Q is just a variable for flow rate, and it's telling you the volume that passes through an area per time. So if we look at this dark blue plug right here, what volume of water, okay, so this is the volume, the dark blue plug, can pass through this dotted line per second. Okay, so that's what a volume flow rate is. It's how much goes through per second. Your reference sheet does not give you this part. Let me get a little pen here. This part of the equation. It also doesn't really give you the rest of this either. What your equation sheet has for volume flow rate is that A1 times V1 equals A2 times V2. And in this case, the V here, notice that it's a lowercase letter. That V is the velocity of the water. So the flow rate is the volume per unit time, but it's also the area of the tube times the velocity that the water is actually flowing through, and that will give you the same units, okay, which is going to be cubic meter per second. Okay, thought that would go away. So this is the equation as written on your reference sheet. A1 V1 equals A2 V2. You will be asked questions about flow rate. Okay, you will be asked about how much volume goes through an area in a certain amount of time. Okay, you need to know, if we go backwards here, that is volume over time, but it's also equal to area times velocity, that those two things are the same. And it's not given to you specifically as volume over time, okay? When a fluid's in motion, it has to move in a way that mass is conserved. Okay, what that means is if I have a really big pipe and it's completely filled with water and the water is moving through and then my pipe gets smaller, my water still has to get through. Water is incompressible. If I have a gallon per minute passing through this area here, I have to have a gallon per minute passing through this area, or there'd be a backup. My pipe would burst. Okay, so whatever mass goes in through A1 has to come out through A2, which means the volume per second has to be the same. And so if you change the area, you change the velocity. Okay, you're going to move slower through your bigger pipe and faster through your smaller pipe to get that same volume through in the same amount of time. So Bernoulli's principle. As the fluid moves from a larger tube to a smaller tube, the velocity is going to increase. And the pressure is actually decreasing when the water moves faster or any fluid moves faster. Okay. The one way you can think about it is there's not enough time for the water to push on the sides of the container, so it doesn't push as hard. Okay, it's moving past that point quicker. And so what you get is a smaller pressure in your faster moving fluid. You can draw a free body diagram for this. Okay. We've got water moving in the rightward direction. And if it's going from here where it's moving slow to here where it's moving fast, my forward arrow on my free body diagram has to be bigger than my backward arrow. Okay, So I have to be moving with a higher force, okay, from the back end of this. If I'm looking at this black dot, the water here has to have a higher force, higher pressure than the water here in order for it to actually accelerate forward. Okay. Obviously, the normal force and gravitational force are going to not change no matter where you are. Okay. So in this case, it's just a little cartoon version of what we just said. This stuff back here is pushing the water forward. The stuff up here is going to push it backwards when you were looking at the water that is right here in this dark blue plug. The water in the back has to push higher than the water in the front. We have to have a higher pressure back here than we do back here. All right. We're going to watch this next time. I'm actually not going to show you this right now. We're going to do some things next time, and then we'll watch it. Bernoulli's principle, okay, can be used in this idea that if we have this tube and this tube is completely filled with water and water's flowing from here to here, then if the pressure is higher in A than it is in B, we should be able to see that by attaching some open air tubes to the top. Because if the pressure is higher in A, it's going to push the water higher up in this tube than B can. And you can see that. This height difference here, just like in the question we did in class on the virtual day, if this water is being pushed higher up against the atmosphere is pushing down on both of these, if this is getting pushed higher up, then the pressure in A has to be bigger than the pressure in B. Okay? And if you take that difference in pressure, PA minus PB, you'll get rho GH. You'll be able to actually calculate it using our pressure equation that we used already. Bernoulli's equation is actually this really long equation, and I crossed off some parts of it for this picture, but this equation's on the bottom, the very bottom of your reference sheet. It is really long. All it is the fluid version of the law of conservation of energy. So P1 is just our external pressure, or the pressure of whatever came before this fluid or this section. 1/2 rho v squared is the kinetic energy. That's the energy of the water as it's moving. And rho GH is the gravitational potential energy. It's the energy of the water because it is going to have some height to it. Okay. And then we have the same thing on the other side. So as we move from P1 to P2, okay, we can go through and look at what's going on. If I look at this, I don't change my height of my water. Okay. When we look at the height of the water, we look at what's called the midline. So we just kind of draw a straight line through the middle of my pipe. And in the middle of my pipe, that line is straight. So I don't have a height difference between this area and this area. Okay. I do have a velocity difference. So if the velocity in 2 is going to be faster than the velocity in 1, then P2 has to be less than P1. If we add tubes at different heights, now we have to add in the extra piece of this puzzle. So we've got the pressure at 1 plus its energy due to velocity, water's flowing through this, right? And its gravitational potential due to height. So we can use it off of the bottom, off of whatever you called ground. You can actually just call the midline of this pipe 0. So we could get rid of that in this and just call this one, how high above this midline. But you have some kind of gravitational potential difference. H1 is smaller than H2. Okay, and then you have P2, which is the pressure at this point, and its kinetic energy. It's law of conservation of energy again. It's just with water in pipes instead of, balls falling from the sky. So as the water loses elevation from the high end of the pipe to the low end, it gains velocity. Okay, we know that. Things that fall are going to get faster. they're also losing gravitational potential energy, okay, and gaining kinetic. To find the exact value of any parameter, we apply the Bernoulli equation to 2 points anywhere along the same streamline. So that's what I was saying, stay right in the dead center of your pipe, and then you can do your calculations. Okay, so a reservoir is 250 meters above the city. Water is transferred through a constant diameter pipe to the city below. Assuming the atmospheric pressure is the same at both locations, what speed is the water moving when it reaches the city? Okay, so a reservoir is a big lake. We consider the water in the lake itself to not be moving. It's sitting still. So at that pipe entrance right here, okay, we're going to consider the water to not be moving. But it is 250 meters above the city. At the bottom, we're going to call it ground level. So we're going to call it 0 meters above the city because it's the city. But now it's going to be moving. It's going to be flowing out of the pipe. So at the beginning, we're going to say that it has atmospheric pressure, okay? Because that's what's up here. Atmosphere is pushing down on this water that is open to the air. So P1, okay, at the top of this reservoir is going to be atmospheric. It is not moving, and it has a height. At the bottom, it's also going to be open to the atmosphere. We're assuming like we just opened the end of the pipe and let it flow out into the street or something, is what the question is kind of saying. So P2 is also atmospheric, but it's now at ground level, so we're not going to use this, and it is flowing. And so we can go ahead and add in the numbers. We had the height. We know the density of water. And even if we didn't, they're going to cancel out on both sides because we're talking about the same fluid. So now it's gravity times 250 equals 1/2 v squared. And what we get is that it's moving at 70 meters per second. Okay. There is another way to do this. The other way to do it only works because the pipe is a constant radius. Okay. And because P1 and P2 are the same because they're both open to the atmosphere. But essentially, guys, this is water that is falling through the pipe. This is literally a kinematics question. But again, only because we have essentially been able to cancel out all the other terms, the P1 and the P2, and the fact that there's no radius change. Okay, but that's kind of what we're looking at. We're looking at using our kinematics and our law of conservation of energy and all the other things that we've learned all year, just now with water instead of a solid object. Okay. Torricelli's theorem, assuming the velocity inside the column is 0, so meaning that the water inside of the cup isn't moving, it's just the water that's flowing out of this that's really moving. The speed of the water as it drains down is inconsequential to the speed of the water as it comes out of these tubes. Then what you have is you have, again, outside pressure here and outside pressure here are the same, so we don't need them. Inside the column, all we have is pressure due to the height of the column, and outside all we have is the kinetic energy. And so what you get is the ability to have this equation now for a situation with a pipe with holes in it, vertical like that. This is the drill we did yesterday, and I tried to say that I needed to really change the question. The largest range is actually from the middle hole. And the top and the bottom ones, if they are equidistant from that middle hole, will go the same distance. And this is the same as when we did, like if we kicked a ball at a 45-degree angle, that was the ball that was going to go the farthest. Because if you look at this hole down here, yeah, it's coming out the fastest, but it has very little time before it hits the ground. This one's coming out the slowest, but it has a whole lot of time to drop, whereas this one kind of splits the difference. So this one, it's got a medium speed and a medium amount of time before it hits the ground, so it actually goes the farthest. Okay, and you can see that here in this little video capture. All right, I'm going to let you take a look at this. I'm going to let you try and think about it, see if you can come up with an answer, and we'll talk about it tomorrow. Okay? All right.